Alrighty, Roo, our first goal is going to be able to state the domain of a piecewise function if I give you its graph. Well, to do that, we probably need to talk about what the domain is. The domain for a piecewise function or any function is what all the possible x values are. What are the values I'm allowed to put into the function? Where does the function actually exist? At x equals 1, do I have a piece of graph? At x equals 2, do I have a piece of graph? These are the kinds of questions we're talking about, okay? So in your little notes, the next thing that should ask you is, what are the 3 questions to ask yourself when figuring out the domain, stating the domain? Here they are. Question 1, does my graph go to the left forever? Does it go to the right forever? And are there any gaps? If you can fill out those 3 things, you pretty much have the domain stated. So I'm going to give you guys a couple of examples. We're going to look at these graphs, we're going to talk about what the domain is, and then how to write it is also important. I'm not going to be a total stickler for the notation you use to write it, but I do want you guys to at least be experienced with this and have seen it before. So example 1, piecewise function, right? I see different pieces. I see a linear piece, a constant piece, maybe something nonlinear, definitely, maybe a quadratic, I don't know, but it's a piecewise function. So now let's ask ourselves those questions. Does it go to the left forever? Sure does. This thing is going to keep going down and left forever. Does it go to the right forever? Sure does. This arrow is indicating that it's going to continue this pattern. It's going to keep going up. It's going to start going up way, way faster than it goes to the right, but it's still moving to the right forever, so yes, it does. Last question, are there any gaps? No. So where does my graph exist? What are the x values? What are the inputs that I can use for my graph? The answer? Anywhere. All numbers work. It goes to the left forever. It goes to the right forever. It's continuous. There's a big fancy word for us, which means there's no gaps in it. That means anywhere. If I plug in a 6, 1, 2, 3, 4, 5, 6, does my graph exist somewhere? It does, right there. What about at -5? -5, yeah, it exists. At 12, at 100, at -50, it exists everywhere. So we would say our domain is all real numbers. I can just say all numbers. I'm not picky. This is called interval notation. It says between negative infinity and infinity. Well, that's all numbers between negative infinity and infinity. And then finally this fancy R. This fancy R means all real numbers as well. Domain, handled. What are the x values? Let's try a different one. Next, looks a little different. We have some different pieces of maybe sine curves, cosine curves, some loopy loops, but ask ourselves the question, does it go to the left forever? Nope. Does it go to the right forever? Nope. Are there any gaps? Nope. Okay, well, how do we put all that into words? Well, it looks like the smallest this graph will ever be is at -5. So all numbers starting at -5, going until I hit 4. We're just talking about x's. Remember, domain are the x values. Those work. Anything between -5 and 4. So we can just say that. Numbers between -5 and 4. Okay. We have to be careful with a couple things. A closed circle means we get to include -5. It's inclusive. That was one of our vocab words. Yes, -5. This open circle down here means that we do not include the 4. It's exclusive. Right up until 4, 3.999999, yes, that's good. But once we get to 4, it actually doesn't work. Okay? So here is the mathematical way to say between -5 and 4. If there's a line underneath this, it's or equal to. That's for closed dots. If it's an open dot, it's just a inequality symbol by itself. So between -5 and 4. Between -5 and 4, including -5, right? I'm talking about that little line. We have to mention that if I'm going to write it like this. And then finally the last way. Between -5 and 4, this is called interval notation. If there's a line underneath it. If it's a colored in circle, it's a bracket, we call that. If it's an open circle, if it's just the inequality symbol, then it's a parenthesis. Any one of those 3 would be okay if I asked you to state the domain. Okay, last one. Does it go to the left forever? Nope. Does it go to the right forever? Yes. Are there any gaps? Yes. Okay, this one is a little bit tougher. So we're talking left and right. What's the smallest, the furthest left I can go and still have graph? Right here. This is as far as left as I can go. 1, 2, 3, 4. -5 is where it starts. And then it picks up until I get to -1. So between -5 and -1, there's graph. There's something there. Then the gap. So I'm going to have to say and then something else. So between -5 and -1. And starting at 1, 2, 3. Looks like it might be goofy, but there's graph there. It's up here at this colored in one, but there's still graph. So 1, 2, 3, 4, 5, 6, 7, on forever. So anything bigger than 1 we'll have graph. Okay, we got to put all this together then and state the domain. This is the toughest one, by the way. If you can handle this, the test will be a breeze for you. Here is between -5 and -1. Colored in circle for the -5, open circle for the -1, and then all numbers that are greater than or equal to 1 or equal to. So this one and moving to the right, or equal to. Okay. This is just putting it in words. Between -5 and -1 works. Including -5 we need to say. But then we also need this, and I ran out of room, so I got creative here. There's my room. And numbers greater than or equal to 1. All right, we're stating domains, letting it rip. All right, moving on.